What's up everybody, I'm back. Welcome to a brand new video, and today we're going to be doing a very different kind of video. This one will be a Godzilla explained, but it won't be the usual kind. Today's video will be a much more science-based episode, and we'll be talking about the physics behind Godzilla's music. Keep in mind, I'm not an expert, so if there's something that I miss out on talking about, or if I mess anything up slightly, don't crucify me, just know it's because I'm not a professional. Godzilla has been an icon of destruction since his first appearance on the silver screen in 1954. From his massive size to his menacing roar, Godzilla struck fear into the hearts of all those who watched as he destroyed Tokyo, leaving it a city of ruins. But one thing that helped Godzilla to stand out from all his other giant monster counterparts, such as the beast from 20,000 Fathoms, was his unforgettable score.
Godzilla!
The original Godzilla was composed by Japanese musician Akira Ifukube, who would go on to score 12 entries in the franchise and numerous other giant monster movies from Godzilla's home studio, Toho Studios. Ifukube became well known for his specific style of writing music. Between his first and last films in 1947 and 1995, his style became so iconic that it is still used in movies as recent as 2016's Shin Gojira. Ifukube's style featured very low and ominous stringed instruments in addition with loud, blaring brass. But why did this style work, and what made it so effective? To understand that, we must first understand some physics. Music is, not surprisingly, composed of sound waves, meaning it moves longitudinally along an oscillating route as it starts in one area, called the source, and moves to another area, called the detector. As the sound is emitted from the source, it moves in all directions, which is why you can hear all of the sound from the Ifukube 100, even if you're not sitting directly in front of the orchestra. Most of the musical devices we are used to hearing from Ifukube, such as his famous bass tones from Godzilla's theme, emit waves called standing waves. Standing waves are called standing waves because they all look like they're standing in place. If you were to see a standing wave, there wouldn't be a noticeable change in anything other than the amplitude of the wave as it moves up and down. These waves move along a path with things called nodes and antinodes. These are visible when you strike strings of a guitar, or the hammer smashes on the wires on the inside of a piano, or when you strike the guitar strings on the homemade harp you built that doesn't work. All musical notes are created as a result of waves being sent down one path and reflecting off something else before reaching back to where it came from, creating an equilibrium. Each musical harmonic is composed of a set of nodes, the parts of the wave that stay the same, and antinodes, the parts of the wave that move. Every time an antinode is added to a set, the harmonic increases. This is how you get different notes. To achieve these notes on a stringed instrument, a simple equation can be followed. It's the length of the string is equal to the harmonic number divided by 2 times the wavelength of the note. Each note has a different wavelength, by the way. The higher octave and higher pitches have smaller wavelengths because they have higher frequencies. The frequency is the pitch. As the frequency decreases, the wavelength increases, resulting in a lower sound. This can be represented by the difference between Mothra's theme and Godzilla's theme. Or the difference between Ifukube's version of Ghidorah's theme and my version of the Ghidorah theme. Once you figure out wavelength and frequency, it is easy to figure out the velocity or speed that the sound moves at, because velocity is just wavelength times frequency. However, if you're in a room of 20 degrees Celsius, the velocity should be 343 meters per second. If you only have velocity and wavelength, you can divide the velocity by the wavelength to find the frequency. Now, the way these instruments work is through a combination of length, mass, and tension. This culminates in musical sound. Tension is important because once you figure out the length of the string needed to play a note at a certain frequency, you must make sure the tension is just right so that the string being struck vibrates at the speed required to achieve the fundamental fundamental frequency, or the lowest frequency needed to achieve a certain sound. This can be found by taking the square root of tension divided by mass divided by length of the string. Then this number is divided by 2 times the length of the string. This is measured in something called hertz, represented with Hz, all sound is. For other instruments in Ifukube's orchestra, such as the flutes and other things we call open pipe resonators, they work a bit differently. Stringed instruments have nodes on each end because they are held in place by something physical, whereas open pipe instruments are open piped instruments. There's nothing to hold them in place in each end, meaning that each end will be an antinode. The first fundamental frequency of an open pipe instrument, much like stringed instruments, is 1/2 of a wavelength. Then it moves up accordingly. This is because as air is pushed through the instrument, the wavelength bounces off each side, the top and bottom of the container, resulting in a different sound being produced. They only get through 1/2 of a wavelength in terms of bounces when looking at the fundamental frequency. The second fundamental frequency, or second harmonic, encompasses a full wavelength. You can use the same equation on an open pipe resonator as you would for stringed instruments, just take away tension. But what about a closed pipe instrument, which are often accompanying Ifukube's strings, such as his trumpets and other brass instruments? These bad boys work to announce the arrival of the military or the appearance of Ghidorah over Mount Fuji, and they work fairly differently than their open-piped counterparts. For starters, closed pipe instruments don't have the same type of wave on each end. The open side, where the sound comes out and is amplified from, contains an antinode, but the part where the person blows into is a node. This means that because of the lack of lining up nodes and antinodes, only 1/4 of a wavelength can make it through for the fundamental frequency, as opposed to the 1/2 from before. Before, the frequency of each harmonic was equal to the number of harmonics times the fundamental frequency. That's still true now, but now you have different wavelengths. For wavelength, you must go from 1/4 of a wavelength to 3/4 to 5/4 to 7/4, and so on. It's not as nice as the 1/2 to 2/2 to 3/2 of wavelengths as we had before. This is the reason why every instrument sounds different than each other. The wavelengths will always be slightly off from one another in terms of closed and open pipes, meaning the sound will be different. Ifukube knew this and was able to use it to his advantage. This is why he was able to have the brass abruptly interrupt the strings and work to create such a different effect than the strings could have on their own in order to announce the arrival of different characters. This is also why, for much more sad moments, he would choose to go with just strings, so that they could work on their own and not have a different sound interrupting them. Ifukube knew that if he were to get the frequencies of music to line up to the point where they didn't work to cancel each other out to create a flat sound, he could then manipulate the way things work to make them sound beautiful. Most musicians know that playing 2 notes directly next to each other in a chord isn't going to sound as good as separating the notes by a third, which is the chord name. As the chords progress, they can be used to create a much more grand sound than they would have on their own. This is why in Ifukube's music, he often used chords of fifths, because the odd numbers wouldn't work to cancel each other out in terms of frequencies. But by using minor chord progressions and using notes that have clashing frequencies, Ifukube knew that it would create a much sharper and scarier sound, leading to themes such as a lot of Gaira's music from War of the Gargantuas and even Ghidorah's theme himself. That's it for this video, guys. If I missed anything or screwed anything up, just let me know down below. I'm kind of an idiot and I'm definitely not a physics ninja, so that's probably gonna happen. Also, if there was something specific you wanted me to mention in terms of Ifukube's music and I didn't, I really do apologize for that. There's a lot to talk about in terms of the way music works, and I couldn't fit it all into one video. Maybe some other time. Thanks for watching, guys. I hope you enjoyed. See you next time. D-Man, out.